Good morning and welcome to this next lecture on sound and structural vibration. Last time we looked at the frequency domain explanation for coincidence phenomenon. This time we are going to take a second example to better understand that. So the second example, example 2, is here. We have two panels vibrating in a certain mode. Okay, so V tilde P sine P pi x by A. Okay, and there is a second panel which is also vibrating in the same mode. Okay, but the second panel is thicker. The second panel is thicker. Okay, and they are vibrating at resonance. They are resonances. So this panel is vibrating at its own resonance 1 n, this panel at its own resonance 2 n. Okay, however the wavelengths are same. This lambdas are same for both. Okay, or P pi by A is same for both. Okay, now if you recall your vibrations of plates and shells, okay, your natural frequency comes out as a square root of d over rho h. Okay, and d carries your E h cube by 1 minus nu square, etc. So it carries an h cube in it. So this h and that h cube becomes h square, and once you bring it out of the square root, this h comes out and other terms remain. So natural frequency is proportional to the thickness of the panel. So the same lambda omega 2n is bigger than omega 1n. Okay, so now what happens is you have a situation where based on this alone, both have Vp tilde sine P pi x by A. Just that expression is same for both, and therefore the wave number domain shape is the same for both. Wave number domain shape is the same for both. Okay, so now the second plate omega 2n is bigger, so the k2n will be bigger. Okay, this is k2n minus k2n. For the first one, k1n is smaller. Okay, so k1n, and you have minus k1n. Okay, and therefore for the first plate you get a smaller range of wave numbers included. Okay, so therefore the power radiated by the first is lower. Power radiated by the first plate is lower, and hence sigma is lower. Radiation efficiency is lower. Okay, now there are cases here. For example, when k approaches p pi by a, that is when coincidence occurs, that means coincidence with the mode occurs. Okay, let's call it modal coincidence. This is different from the coincidence of the full plate where k is equal to kb, the free wave number is different. Okay, it's just here k is equal to p pi by a. Okay, so when k approaches p pi by a, that's the coincidence with the mode. Okay, and once it crosses p pi by a, then you get a very large range of wave numbers within radiation, and the radiation efficiency is 1, is close to 1. Okay, now within that, this panel could have a resonance below here, could have a resonance here, its resonance here, or it could have its resonance beyond. Okay, so we will see those cases later. Okay, here let us see the simple example which just illustrates that based on the omega you could include larger or fewer number of radiating wave numbers. Okay, this is a scattering phenomenon. Okay, because you have a finite panel with a certain wave number in it, that finite wave number scatters into all these extra wave numbers. Okay, so we are just illustrating that even below coincidence, these are all below coincidence now, right? Coincidence happens here. So below coincidence, because of the finiteness of this panel, there is radiation possible because of this, all these scattered wave numbers. Okay, and within that, being below coincidence, within that range, we have taken examples to show how you could have more radiation or less radiation. Okay, and especially if you have a resonance within this range, okay, suppose that omega n as it happened over here, then this value will be bigger actually. Okay, this amplitude will be bigger because Vp will be bigger. Okay, so you will get more radiation. Now this should also give you a hint as to why we have not allowed Vp to change. Okay, we have not allowed Vp to change. That has helped us in doing these comparisons. Vp also changes, that complicates, but now I have added that line that you could have a resonance in this range, you could have a resonance in this range. Okay, and that would help you further. Why? Because these wave numbers will grow in their amplitude, will have a higher amplitude, Vp will be higher. Okay, just with this last statement I have allowed Vp to change with frequency. Okay, so now as I said, the extra cases which come up with coincidence versus resonance, resonance being above coincidence or below, we will see those now. Okay, and before doing that let me do all the other cases for a 2D panel. So this time from 1D we move to 2D, and we will look at it in the wave number domain. So let us see the cases in a 2D panel in the wave number domain. So we have, okay, this is the kx axis and this is the kz axis. Okay, and let us say that p pi x by a is here. p pi by a is here, and here is my q pi by b, q pi by b. Okay. Now let us draw on top of this the acoustic wave number circle, K circle. Okay. So if we draw that, and let's say I draw it here, this is where it is. Okay. And the remaining scattered wave numbers look like this. Okay. So this is a case where K happens to be greater than q pi by b, but less than p pi by a. Okay, which means lambda, okay, is less than lambda z, structural wave number, and lambda is greater than lambda x, structural wave number. Okay, that's how the plot looks like. Okay, this is one case. This is one case. Okay, so let me give a name here. Let me give it a name Z edge mode. This will make sense later. Let me give it a name Z edge mode. Okay. Now the second case, case 2, is case 1. Case 2, we have in this case p pi by a comes closer, and q pi by b is big away. And this is my K circle. Now in this case K is less than q pi by b. Okay, so lambda is greater than lambda z structural, and it is greater than p pi by a, and lambda is less than lambda x structural. Okay, so I will again give this a name, call it X edge mode. Okay, now the third case will be where we have this situation. Okay, so this is p pi by a, this is q pi by b. So K happens to be greater than q pi by b, it has to be greater than p pi by a, and therefore lambda is less than lambda z, lambda is less than lambda x. Okay, Okay, so we'll give this two names. We'll call them double edge, or we'll call these double edge, okay, or XZ edge. Okay, or I'm just saying an or, we'll call it acoustically fast modes. Okay, in the last case is here, fourth case is here, where we have the acoustic circle and the P pi by A peak lies here, Q pi by B peak lies here. Okay, which means K is less than Q pi by B is less than P pi by A, which means lambda is greater than lambda Z structure, lambda is greater than lambda X structure. Okay, we'll call these the corner modes. Okay, these situations occur. Okay, now I will show this on an actual panel. Okay, let us see this on an actual panel. So we have a panel here, we have a panel here. Okay, 1, 2, 3, 4, 5, okay, then 6, 7, and we have okay, so we have 7 cells here, we have 4 cells here. Okay, so this is, let's say, my X direction, let us say this is my Z direction. So this is a panel, or a plate. Okay, this total is A, this total is B. Okay, now this happens to be the, let me change color, this happens to be the lambda X. Okay, so this now happens to be this, let's say this happens to be lambda Z, this happens to be lambda Z. Okay, and let us now assume, okay, that my lambda, the acoustic lambda, is slightly longer. Okay, slightly longer than lambda X and slightly shorter than lambda Z. So that means lambda Z is bigger than lambda and lambda X is shorter than lambda. Okay, that means what? If lambda Z is bigger than lambda, that means Kz is smaller than K. Okay, so with respect to Z modal wave number, we are above coincidence, and lambda x is less than lambda means k x is greater than k, which means we are below coincidence with respect to x. Okay, so there is going to be now cancellation. There is going to be now cancellation. And how will the cancellation occur? So let us see. We have, let us take blue color. Okay, let's take the blue color. Okay, let's take the blue color. Now this part will cancel with this part. Okay, this part will cancel with this quarter. This quarter cancels with that quarter. This quarter cancels with this quarter. This quarter with that quarter, and a portion remains uncancelled. So now this entire portion like that will remain uncancelled. This entire portion will remain uncancelled. That means this region on the plate. Similarly on this side, this entire region will remain uncancelled. Everything in between will cancel. Okay, so this leads to Z edge modes. Z edge modes. Okay, so what am I saying? A mode when vibrated at a certain frequency omega, which gives you a certain acoustic wave number k, okay, with fixed kz, or I mean kx and kz fixed, okay, it ends up looking like a Z edge mode, provided these relations hold. Okay, and that's why I gave it the Z edge mode name. Okay, so lambda here is less than lambda z, so along z there is no cancellation, we are above coincidence. But in the x direction the lambda is greater than lambda x, so we are below coincidence, so cancellation occurs. And how does it occur? It occurs in these nice rectangular patterns. Okay, so that mode becomes or behaves like a Z edge mode, and these two edges will radiate. Okay, similarly you could have a situation, I will not redraw it again. Okay, so similarly you could have a situation where lambda z is smaller and lambda x is greater, and therefore kz is greater and kx is smaller. Okay, that means here we are below coincidence with respect to z modal wave number, but with respect to x modal wave number we are above the coincidence. Okay, so what will happen is we will have x edge radiators. We will have x edge radiators. Okay, we will have x edge radiators. Okay, now along the same lines you could have a situation where, okay, lambda z happens to be less than lambda lambda x also happens to be less than lambda, which means kz happens to be bigger than k, kx happens to be bigger than k. Okay. So then you will have cancellations happening in both the directions. Okay. And what will happen is, I will just show you again a schematic. Okay, let us say 1, 2, 3, 4, 1, 2, 3, 4, let us say. Okay. So if we take now the mode behavior, and the mode behavior in this direction, these are supposed to be equal length scale cells, but don't mind. What will happen is cancellations will occur here. Okay, each neighboring quarter cell, but one quarter cell will remain uncancelled here. Okay. Similarly, one quarter cell. Similarly, everything else will cancel here. Okay, except one quarter cell will be left, and similarly one quarter cell here. So in this panel there will be a quarter cell here, quarter cell here, quarter cell here, and quarter cell here. So this is the corner mode. It's the corner mode. Okay. So let us see now the progression a mode, suppose there is a mode. Okay, now let me write it in some way. V tilde pq sine p pi x by a sine q pi z by b. Okay, and again we keep vpq constant. By now you know why we do that. Okay, if that also starts to change, then it's a very complicated situation. Okay, you know from plates and shells that the denominator is of the form omega square minus omega square pq. Okay, so now as omega starts to shift, it will get closer or distant from omega square pq, and the vpq will start changing very non-linearly. So we avoid that by keeping this term for the moment out, and so we keep v tilde pq constant. So now this mode now excited at a certain frequency, which we will vary to see the effect. Okay. So at very low frequencies, k is less than kx, k is less than kz. Okay. Similarly, the lambdas are greater correspondingly. So we will get this picture. We will get this picture. That mode is a corner mode to start with. It starts off as a corner mode. Let me partition it. Corner mode. Okay. Now I just drawn almost a square plate, but you could actually have it rectangular in one direction or the other. Okay, A could be bigger than B, B could be bigger than A. Okay, so this is more representative of an actual plate, but I just drawn it almost square. Don't worry about it. Okay, now as frequency increases, Okay. I think that time is up, so I'll stop here. We'll continue in the next class. Thank you.